Electricity is vital to our civilization. So what is electricity and how does it work? To explain electricity, we need to zoom past the molecular and into the atomic level. Atoms are the smallest things we can kind of see, but not with the naked eye. Only with a scanning, tunneling microscope can we get a glimpse of somewhat fuzzy spheres. To really understand electricity, we must go even further and look inside an atom. This is where it gets complicated, because the inside of an atom cannot be seen, at least not at the time of writing. So we will use this representation of the inside of an atom. This is called the Bohr model. Keep in mind that it is not to scale and only two-dimensional. This model is also known as the planetary model, modeling the parts of an atom as planets orbiting a sun or moons around a planet. While actually these orbiting moons are not at any one place at any one time at all, but exist more as regions or clouds around the core. However inaccurate the Bohr model might be, it will do for our explanation of electricity. Atoms consist of protons and neutrons. These form the nucleus of the atom. Orbiting the nucleus are the electrons. It's these electrons that are responsible for electricity, hence the name. Think of these orbits more as shells surrounding the nucleus. What type of atom, which element it is defined by the number of protons in the nucleus at the center. Atoms of one element all have the same number of protons, but can have different numbers of neutrons and electrons. It's this variable number of electrons that is important to our understanding. Electrons, which are far lighter than the protons in the nucleus, can relatively easily move. And this is important because the movement of electrons is what forms an electric current. The atom's protons account for the positive charge of the nucleus, and the electrons for the negative charge. In a stable resting, or rather neutral electrical condition, these charges balance each other out within the atom. This gives the atom a net electric charge of 0. For each positive proton, you will find one negative electron. In this state, the atom is at its lowest possible energy level, which we call the ground state of the atom. However, we can change the atom's charge or energy level by causing it to gain or lose electrons. When the atom has fewer electrons than protons, it becomes positively charged. But when the atom has more electrons than protons, the net charge swings back the other way and it becomes negatively charged. More electrons than protons mean the atom is negatively charged. Fewer electrons than protons mean it is positively charged. Losing or gaining electrons changes the atom's electric charge. The remainder of this video we will color code the atoms as follows. A positive charge or absence of electrons is represented with red. A negative charge, a surplus of electrons, is represented with blue. A neutral charge, or a balance between electrons and protons, is represented by a blend of red and blue, purple. So when in a ground state or uncharged, it looks like this, and it's called an atom. When charged, negatively or positively, it looks like these. Instead of atoms, when there is a charge, these are called a negative or positive ion. Each shell of an atom can hold a maximum number of electrons. The inner shell can hold 2 electrons, the second can hold 8, the third 18, and there are elements with all 7 known shells. Shells are populated with electrons from the inside out, meaning that added electrons always go for the innermost shell possible with a spot left. The number of electrons on the outermost shell determines the reactivity of the atom. This shell is called the valence shell, and its electrons are called valence electrons. When the outermost shell is full, the atom is generally stable and least reactive. You may be familiar with the term and effects of static electricity. When you, for instance, shuffle your feet over a nice soft carpet, you build up a positive charge, because negatively charged electrons are being lost to the carpet. Carpets are often made from a material with the properties of an insulator. Insulators do not easily give up electrons but can get a local charge when electrons from a conductor are rubbed off on them. An insulator's valence shell is already quite full of electrons. These electrons will just sit there until something else takes them away. However, your body is a conductor. Conductors have loosely bound valence electrons, which are easily transferred or lost, in this case from your body to the area of the carpet where you're shuffling. Instead of you and the carpet having a neutral charge, a charge imbalance is being created between you and the carpet. Now, when you touch a metal object, for instance a doorknob, you get zapped. The doorknob may be neutrally charged, it is metal, and metals too are conductors with loosely bound electrons on the outer shells of their atoms. These electrons immediately move to your body to restore the charge imbalance, giving you a jolt. Nature always seeks a neutral charge equilibrium, a net charge of zero. Materials with high electron mobility are called conductors. Materials with low electron mobility are called insulators. A commonplace object where you can see an insulator and conductor working together is in a simple wire. This electrical wire has a copper core and a plastic shell. Copper atoms have a very loosely bound electron on the outside, as seen here again using the Bohr model. This makes copper a perfect conductor, whereas the plastic is an insulator. The millions, if not billions, of copper atoms in this piece of wire easily exchange electrons, allowing us to make an electrical circuit with it. Think of an electrical circuit as a path that connects two points with a possible charge imbalance, usually connecting a negatively charged point to a positively charged point. Like marbles in a tube, moving from a high place full of marbles to a low place lacking marbles. Imagine these marbles all along the circuit, each marble being an electron. These marbles originate from a power source, for instance a battery. And we'll explain how batteries work exactly in a future video. Electrons move from the negative to the positive, as we've established earlier. The battery pushes out electrons from one end and attracts them from the other. As one is pulled in, one is pushed out. Despite the electrons moving relatively slowly, this effect causes the energy to be transferred almost instantaneously. To create such a flow of electrons, we must provide them a path with a conductor, such as the copper within our wire. If this path is blocked by an insulator, such as plastic, rubber, or air in the case of a cut wire, the electrons cannot continue to flow, stopping the electric current. The key to the flow of electricity is making a continuous electrical circuit, connecting a wire between a source of electrons and an attractor of electrons. All electrical devices are powered this way. That is why your battery has two poles, a source and an attractor, a negative and a positive. This is also why your electrical plug has at least two tongues, one for incoming electrons, one for outgoing. You see, electrons are not spent, they do not cease existing. They are mere carriers of charge and can only be useful on their way to their destination. Take note that connecting two poles of a power source directly can actually be very dangerous. This is what's called a short circuit, because there is nothing between the source and the destination of electrons to power, such as a lamp or television. This means that the electron flow will not encounter any resistance. The release of energy when short-circuiting is therefore instant, often paired with the involved wire heating dangerously. This is why buildings and some devices have fuses. These automatically cut the current flow when the current becomes too high, preventing damage or worse,